Okay, good morning, everyone. Let's start today's seminar. Today's seminar speaker is Professor Lam Hui from Columbia University, and he will talk about wave dark matter. Please start.
Thank you. Thank you for the invitation, Dongwu, and thank you for the opportunity to speak to you. Today, I want to talk about work that I've been doing in the last few years. I have a fairly large number of collaborators. I won't be able to go through everything listed here. Maybe for the first 10 minutes, the introduction part of the talk, it will be mostly based on the first paper with Jerry Oestreicher, Scott Tremaine, and Edward Witten. And then the bulk of the talk will be based on actually the fourth paper with Austin Joyce, Michael Landry, and Xinyu Li, and it's on the subject of vortices. In case you are curious about the more general background, I recently wrote a review article and it's given in the last reference. You can find that on the archive. It's a review article. Before I start, just a little bit of advertisement. Is something that I am actually fairly excited about, but it's not the subject of today's talk. It's a paper that we put out last week on certain symmetries, we call ladder symmetries of black hole perturbations. If you are interested, please take a look at this paper. Unfortunately, I won't have the opportunity to talk about it today. So let me go to the main topic, right? So this slide is probably unnecessary for this audience. By now, we have fairly compelling evidence for the existence of dark matter. And the astronomical evidence, as you know, is basically from its gravitational effects. And there are many, by now, many different kind of measurements, all pointing towards the existence of dark matter. So in this talk, I'm just going to take it for granted. Despite the compelling, the rich evidence, we have very little idea what dark matter is, as you know. For example, an illustration of our degree of ignorance is we don't even know if dark matter were a particle, what kind of mass does a particle have, right? So here I give a very huge range, this spectrum, all the way from 10 to the minus 22 electron volts to basically astronomical size. This is like 10 solar mass. And if you look at the literature, there's really all kinds of proposals that span this whole range, which is just to say we have no idea what kind of particle dark matter is and what is its mass, for example. On this very vast spectrum, though, there is one scale that we can put down, which is sort of an interesting scale to think about. And it comes from basically the following observation. What we do know from data is the mass density of dark matter. For example, in the solar neighborhood, the mass density is around 0.3 GeV per centimeter cube. And from this one single number, we can ask the following question. And the question is this. What particle mass would it be such that the inter-particle separation would be smaller than the de Broglie wavelength? Okay, let me repeat the question. No? At what dark matter mass would the interparticle separation be less than the de Broglie wavelength? Okay, a little bit of an unusual question, but we can ask that question. And I'm going to skip the math. Knowing this number, 0.3 GeV per centimeter cube, we can answer that question, which is this one. And remember that the Broglie wavelength depends on velocity, right? And here in this talk, I'm going to take the velocity dispersion of the Milky Way. So that velocity is around 200 kilometers per second. Okay. And we can answer this question is actually around here. It's around 30 electron volts. If your dark matter particle mass is less than this number, you are in what I would call the wave regime. What do I mean by that? It means something like this. So this is my little cartoon. So suppose I draw a sphere where the radius of the sphere is the de Broglie wavelength. If you are anywhere less than 30 electron volts, you are essentially in a regime where you have multiple particles within your de Broglie volume. The smaller mass you have, the more particles you have in the de Broglie volume. And first of all, that tells you this particle must be bosonic. It cannot have multiple occupancy if it were fermionic. So in this talk, we will be talking about the bosonic particle. In particular, in this talk, we will be focusing on the spin zero aspect, although many of the phenomenology I'll go over applies to spin one or spin two. Okay, we will focus on spin zero, bosonic. And furthermore, what do I mean by the wave regime? Well, we are in a regime that is very similar to what we know in classical electromagnetism, right? If you have a state with a high occupancy, many photons, very often it is the case that such a state is well described by basically classical waves, classical electric and magnetic fields. So that's basically what I have in mind when I say we are in the wave regime. So in this talk, when we say wave dark matter, we are going to be talking about classical wave phenomena, which is applicable to a state with high occupancy. Now, to give you an idea of the numbers, so I sketch out, give you some examples of the de Broglie wavelength for several different mass scales. If the mass scale is around, let's say, 10 to the minus 6 electron volts, you might, as you might know, 10 to the minus 6 electron volt is the target mass of some axion detection experiment. For example, ADMX, a microwave cavity experiment. That's around the target mass, 10 to the minus 5, 10 to the minus 6 electron volt. If you work out the de Broglie wavelength, it turns out to be some fraction of a kilometer. It's actually pretty big, meaning 10 to the 4 centimeter is certainly a lot bigger than the size of the experiment, for example, of the microwave cavity. It's not quite astronomical, but it already tells you there are interesting wave phenomena, even for let's say, an axion dark matter detection experiment, which I hope to talk about. If you go to the ultralight, in this talk, when I say ultralight, I mean something like this, around 10 to the minus 22, within 1 or 2 orders of magnitude of that. And in that case, the Broglie wavelength will be truly astronomical, meaning it's a sizable fraction of a galaxy or a small galaxy. And as you can imagine, if you are in this ultralight regime, there would be interesting astrophysical consequences, which we will also go over. But for most of this talk, most of what we have to say would apply as long as your dark matter mass is less than about 30 electron volts. Okay, but occasionally we'll specialize to in some particular masses, 10 to the minus 6 or 10 to the minus 22, when those examples come up. All right, and here is a brief outline. So we are going to spend the next 5-10 minutes talking about particle physics motivations, why we might be interested in the dark matter particle that is fairly light, in particular a scalar particle. And then most of the talk I'll focus on the second aspect, basically talking about the dynamics and the phenomenology. And towards the end, I will talk about the astrophysical implications. They are mostly relevant when the dark matter particle mass is ultralight, around 10 to the minus 22. In fact, in this mass range, as you probably also know, the dark matter is often called fuzzy dark matter. So sometimes I'll use that terminology. But I also want to spend some time towards the end talking about experimental implications. By experiment, I mean dark matter, or in particular axion detection experiments. In that case, the target mass is often not ultralight, but it's light enough that we are in the wave regime, and we'll talk about that as well. Okay, so this is a brief outline, and I should say I would welcome very much questions. If you have questions, please speak up and let me know, interrupt me. In fact, maybe now is a good time to just pause in case you have questions. I'll pause from time to time for questions. Okay, I'm going to now talk about motivations. Okay, so this part will be very brief because these are things probably you know well. And a fairly natural candidate for a light spin zero particle is of course a pseudo-Nambu-Goldstone boson. And here I put a little cartoon here to kind of remind ourselves this is a Mexican head potential. There's a U1 symmetry, and the vacua is basically this circle in the bottom here. And if you pick any particular value along this circle, you have broken the U1. So you have a Goldstone boson, which is basically the angular field. In this talk, I'm going to call that phi, is an angular field. And very often non-perturbative effects actually breaks the U1 slightly. So the U1 symmetry is not exact and is basically equivalent to taking this Mexican head potential and tilting it a little bit so that you actually have a mass. Hence the name pseudo-Nambu-Goldstone boson, right? The most well-known example is, of course, the QCD axion. And it was not originally invented to solve the dark matter problem. It was invented to solve the strong CP problem, as we know. But later on, it was appreciated that it might be a good dark matter candidate. Unfortunately, I don't really have time to go into the physics of the QCD axion. So I'll just leave that topic as that. I should just add a comment. More generally, in a theory like string theory, there are many axion-like particles, where these axion-like particles, for example, in string theory, they arise as zero mode or Kaluza-Klein modes of some higher form fields when we have compactified dimensions. I do want to mention one particular corner of the parameter space where the numerology is kind of interesting. So let me mention that, right? So this is what I want to say in this part of the talk, where it turns out there is some motivation to consider an axion or axion-like particle that is ultralight. And the story goes something like this, and it goes by the name of basically misalignment mechanism. So let's consider the following, right? So I have this angular field phi, which if we were a strict Goldstone boson, it should be massless. But non-perturbative effects, such as from an instanton, for example, would generate a potential of this form where the energy scale lambda here typically is exponentially suppressed by some moderate size instanton. And so this lambda can be very small compared to your fundamental physics scale. The potential still is periodic because it's an angle. This phi is an angle. The periodicity scale, which I call F here, is usually called the axion decay constant. And if you expand out this cosine around phi equals 0, you can read off the mass scale for phi. M square phi square term tell you the mass is of this order. And the reason why this particular mass is interesting comes from thinking about the radic abundance from the Big Bang, using what is often called the misalignment mechanism. And the story probably is familiar to a lot of you, but let me just say it very briefly. Let's say the axion field phi has some primordial value in the early universe. And absent any information, a very natural value to choose for phi is the axion decay constant itself. That is kind of the natural scale, or if you like, phi over f, which is a dimensionless number. The actual angle is order 1. Okay, so we say a misalignment angle of order 1. That seems like a natural assumption to make. If you make that assumption, so this phi will sit somewhere here This is the potential that I sketch out. This V of phi is basically this potential. The blue dot here illustrates the primordial value. And because in the early universe, the Hubble expansion rate is fairly fast, the field basically does not roll. Hubble friction basically hold the field value at this primordial value until when the Hubble expansion rate, H, drop to be around order M, which is basically the curvature scale. And at that point, the scalar field now can start to roll down the potential and in fact oscillate around the minimum, around 0. And with the Hubble expansion, in fact, the oscillation energy of the scalar field get redshifted, as you know. And so the oscillation get closer and closer to the minimum. And in fact, when you're sufficiently close to the minimum, you can even forget about this whole cosine structure. You can well approximate the potential as just m squared phi squared. And if you work out the energy density in these oscillations, that energy density redshift like 1 over the scale factor cube, meaning it redshift just like any non-relativistic matter. So from that point of view, it's already a good cold dark matter candidate if you want. What is interesting is if you follow this story, I'm skipping some math here, but if you follow this story, you can show the radic density, omega, in the dark matter abundance. You can think of these oscillations as basically representing a collection of particles if you want. And the radic abundance in these particles is around what you need to account for dark matter. If you make two assumptions, one assumption is the axion decay constant is relatively large, 10 to the 17 GeV. This number was not completely pulled out of a hat. It's a number that seems to be fairly typical in string theory constructions, somewhere around Getz scale to Planck scale, somewhat large axion decay constant. And if the mass of the particle, this m, is actually fairly light, ultra light, around 10 to the minus 22 electron volt, right? I should say though, if you look at this expression, it's clear the radic abundance is more sensitive to our choice of f than our choice of m, right? It goes like f squared, m to the 1/2. And so really, if we want to be precise, this m can have quite a wide range too. If you want to just restrict yourself to a case where, okay, this make up the entire dark matter abundance. If you shift around the axion decay constant a little bit, keeping the same abundance, m can actually take a fairly wide range. So keep that in mind, right? Nonetheless, this argument does seem to suggest that we should think about an axion or axion-like particle that's rather light. It might not be exactly 10 to the minus 22. It might not be that light, but in any case, rather light. So that's if you want, it's just a hint for us to think about wave dark matter. I should also say this story that I sketch out is in fact very well known. If you look at the classic papers, which are listed here for computing QCD axion abundance, these papers actually computed it also using the misalignment mechanism. The only difference between the calculation that I show you here and these classic calculations for QCD axion is that in the case of the QCD axion, the potential is temperature dependent. Here, I actually make it even simpler and assume the potential is just fixed from very high energy and temperature independent. But otherwise, it's really the same calculation. Let me pause here for a moment in case there are questions.
Hi, Lam.
Yeah.
Maybe a question or comment that this regime is also interesting in another way, which is that basically this is probing quantum gravity in some sense, in that you have this combination of the instanton suppression factor, the action of instantons, and and the decay constant. And if you multiply them, you get in this regime basically the Planck scale.
Yeah, that's right.
And it's something similar to the mass times the gauge, no, mass over the gauge factor in a particle. And it suggests that these are like black holes in a sense, these instantons that create this potential. And it's a regime that on the one hand is interesting, on the other hand is dangerous to trust some of these computations.
That's right. That's right. Yeah. In fact, you are close to. You're actually somewhat close to this bound that one can put from basically, if you want, a weak gravity conjecture.
Exactly. That
Exactly.
was. And the reason that it arises in string theory is because precisely string theory treats this as extremal objects, which is what the weak gravity conjecture treats.
Yeah, that's a good point. That's a good point. Thanks for bringing this up. Yeah, absolutely. Other comments or questions? Once again, I welcome a lot interruptions, so please interrupt me anytime you wish. So in any case, just to summarize what I said here, we seem to have, at least from a particle physics perspective, reason to think about, let's say, a spin zero particle that is rather light enough to be in the wave regime. In fact, deep in the wave regime, for example, if it's 10 to the minus 22 electron volts. Okay, so that's our particle physics motivation, if you want. Okay, so let's talk about the dynamics, right? In light of what I said, the dynamics is actually incredibly simple because as I was saying earlier, the potential you can just approximate as m squared phi squared. There will be phenomenon where you want to actually keep track of the self-interaction of the axion. If you expand out the cosine, of course, there's a phi to the fourth term, for example. It is there. And there are some actually situations in which you should actually think about the self-interaction. In this talk, mostly we will ignore those situations. As far as structure formation is concerned, most of what is going on, you can capture by just thinking about basically a free massive scalar with mass m. So it obeys the Klein-Gordon equation. And in fact, one further simplification, if you want, is if you think about the Milky Way, for example, the velocity is around 200 kilometers per second, so clearly it's non-relativistic. And in that case, it's very useful, as you know, to switch to a different description where you introduce a complex scalar, which I call psi here. Phi is a real scalar, our original axion. Psi is a complex scalar where the trick is you factor out this phase, right? This is e to the IMT phase. That m is just really the rest mass of the particle. And that's what the Klein-Gordon equation tells us. The primary time dependence is this frequency m. So you factor that out, and then you assume this psi, whatever time dependence it has, is much weaker, meaning it has a time dependence that is on longer time scale compared to this frequency m. With that assumption, it's very easy to show. It's very standard. You go from the Klein-Gordon equation to the Schrödinger equation, which I wrote here. And the only interaction that we are going to keep track of for the majority of this talk is gravitational. So I include here the gravitational potential. And the gravitational potential, I should say, is sourced by the axion field itself, right? So imagine you are in a situation you are dark matter dominated. And so not only do you have the Schrödinger equation, but you have a second equation that I should have written down here. I forgot to. The second equation is really simple. It's the Laplacian of the gravitational potential is sourced by basically psi squared. Psi here, if you square it, it's like the wave function. You square it, you get the number density. You multiply by the mass m, you get a mass density, and that sources the gravitational potential. Okay. And so the dynamics, to summarize, is very simple. It's just two equations. One is the Schrödinger equation with this gravitational potential. And then the second equation is Poisson equation that tells you the gravitational potential is sourced by psi squared. Okay. And I'm going to refer to psi as the wave function because this really looks like the good old Schrödinger equation. But I want to caution that despite the appearance of the Schrödinger equation, what we are dealing here really is just classical waves. Yeah, we are in a regime where we have high occupancy, many particles in the state, and therefore this psi really should be thought of as a classical complex scalar. The quantum fluctuations in principle, they are there, but they are very suppressed, as you know, when you have high occupancy. Okay, so that's the regime we are interested in. There is an alternative point of view, which is actually useful for conceptual understanding, is to think of this system as describing a fluid. And the way you think about it as a fluid is to do the following decomposition, right? You have this complex scalar. You can decompose it into an amplitude and a phase. The amplitude we would naturally associate with the square root of density, right? As I said earlier, the density is nothing other than the mass, the rest mass times psi squared. And so square root of the density is the amplitude of the wave function. How about the phase? The phase, which I call theta here, it turns out you can associate that with the velocity potential of a fluid. So if I define a fluid velocity as the gradient of the phase divided by m, you can show you have the analog of what you would call mass conservation in fluid mechanics. And this mass conservation equation should be very familiar because if you think about the Schrödinger equation, of course, in quantum mechanics, we would say there is probability conservation because this equation has a U1 symmetry. So that's probability conservation. And that, in this fluid picture, translates into mass conservation. And by the way, I should also say, the U1 symmetry here should not be surprising. The U1 symmetry here follows from the fact that we are taking non-relativistic limit, right? In the non-relativistic limit, we are not creating or destroying particles, the axions. And so we have particle number conservation, right? And so that's really the origin of that U1 symmetry in the Schrödinger equation. And once again, in the fluid picture, it gets recast into mass conservation. Now, the Schrödinger equation is a complex equation, so there should be two independent equations. And in addition to mass conservation, the other equation is actually the Euler equation, which is also familiar in fluid mechanics. And most of the terms here should be very familiar. The left-hand side basically tells you the fluid acceleration, the acceleration of a given fluid element. The right-hand side, the first term is just gravitational acceleration, right? Gradient of the gravitational potential. The last term may or may not be familiar with you. In the literature, it's often called quantum pressure, although in our particular context, it's actually neither quantum nor pressure. It's not quantum, again, because even though we have the Schrödinger equation, we are really talking about a classical phenomenon. In fact, in detail, if you think about the form of this term, it's not even pressure. If you compute the T mu nu, for example, of this fluid, it has off-diagonal components. It's more like some kind of stress. And the form of the stress precisely take the form that in the Euler equation, it gives you this term. I'll occasionally still call it quantum pressure because that term has kind of stuck. One useful thing about this way of rewriting is it kind of makes it manifest in what sense the large mass limit, when you take m to be big, you kind of go back to the particle regime instead as opposed to wave regime. Because if you look at this equation, the Euler equation, imagine m is big such that you can ignore the last term. The surviving terms in the Euler equation is exactly the same equation you would use to model conventional particle cold-dark matter that basically do not interact except via gravity, right? Basically pressureless cold-dark matter. Okay, so this term actually make that obvious. Of course, in this talk, we are precisely interested in the opposite regime. We are interested in regime where this particle, where this term cannot be ignored. And there are lots of interesting wave effects. That's what we want to consider. Let me pause here in case there are questions. So the basic dynamics is basically described in the equation on this view graph. There's really not much more than that. What is interesting is there is a very rich set of phenomena that follow from these equations. So that's what I want to kind of spell out for you next, right? So what kind of wave phenomenon am I talking about? Maybe I'll just skip this slide. This slide is purely to quote authority. This is Feynman lecture, volume 3, where actually I think it's the last chapter in that volume. You can look it up, where Feynman has some helpful discussion on to what extent you can think of psi as classical. And in fact, in the same chapter, you will find that quantum pressure term if you look at it. Okay, I'm going to skip that. Just a little bit, maybe one word on the literature. There is, of course, a very large literature, and I'm not even covering, probably I'm missing a lot of papers. There's a long history of thinking about dark matter as scalar field. And in fact, here I'm even missing all the whole literature on axion in particular, right? And so I should say that, number one, there's a long history of people working on scalar field as dark matter. In particular, there is a subset of the literature that focuses on dark matter as some sort of superfluid. And I listed some of the papers here. Maybe to orient you, a lot of these papers that talk about the dark matter as a superfluid, what they actually are interested in is a regime where the self-interaction of the scalar field plays an important role, which certainly can happen. In this talk, if you want, our superfluid is kind of a minimalist version of that. It's a version where the self-interaction is unimportant, okay? So we basically ignore the self-interaction. There would be situations where you might actually want to include the self-interaction. But for typical axion models, if you apply to structure formation of galaxy dynamics, very often the self-interaction can be ignored. So we are in that regime, okay? Okay, so what kind of wave phenomena am I talking about? I think this view graph should make it clear. This is a snapshot of a cosmological simulation. So you start from just small fluctuation in the early universe, Gaussian random fluctuation, and then you just evolve the equation that I just showed you with gravity. And over time, you see this interesting feature. You see this interference pattern. I'm going to play a movie actually so that you can see the three-dimensional structure more clearly. This is not a movie in time. This is just taking the three-dimensional box at late time and just doing slices across the box. And I hope it makes clear that you can see these, for example, here is a halo or a proto-halo. This is another halo. There's a filament connecting them. So these are features that you will see even in particle cold-dark matter. But the wave feature, I hope is also obvious. You can see these interference fringes. What is going on there? Well, what is going on is actually very easy to understand, right? Suppose I have a halo and I have superposition of waves inside this halo sloshing around. These waves in general would have random phases. And occasionally you are going to have constructive and destructive interference. It's basically impossible to avoid. It's a generic prediction of having wave dark matter. And the rest of this talk is really going to be about this wave interference pattern. That's what we want to focus on. In particular, as you will see, it turns out to be very interesting to study places where the destructive interference is complete. And when I say complete, I mean the following: that destructive interference of waves means in those places when it's complete, the density in fact go all the way to zero. That's what I meant. You might be surprised why I even want to focus on that. It turns out to be a very generic phenomenon. So I'll explain that a little bit more in 5-10 minutes. Okay, so that's what we will focus on. Let me also say there has been a lot of work actually putting that system of equations on the computer. The first set of authors that point out that there are these really very nice, interesting wave phenomenon, interference phenomenon, was pointed out in this paper by Shai, Chiu, and Broadhurst, followed by many others, including ours, our work. Okay, so let me give you just a kind of a partial list, right? So because of this wave phenomenon, there are actually a lot of interesting places that one could look for these kind of wave effects that kind of distinguish wave dark matter from particle dark matter. So we have looked at a number of them. I'm going to focus on some more recent work. So these are more recent work done by us, and due to the lack of time, the limitation in time. Let me actually check the time. Okay, so I have about maybe 20 minutes. So I'm going to focus on vortices. I don't think I'll have time to talk about these other aspects. So let me go to vortices. Let me just pause here before I go on to this topic of vortices in case there are questions. Okay.
Hello.
Very good. Yeah.
Hi, Lam.
Hi.
This is Jia.
Hi. Thanks.
I want to ask. So, for example, in this figure, I noticed that the scale of this lens is quite small. It's a very small scale. In the case that if we only have the resolution, for example, only resolve into like 100 kpc per pixel, what do you think will the phenomena be?
So what axion mass are you thinking about?
So the same as what you have illustrated here.
So you mean in this particular case?
Yeah, in this particular case, because I can see that this scale is actually quite small. So observationally, maybe we cannot really observe so much detail if we are thinking about a bit higher redshift. So if it's a very low resolution, for example,
yes.
Then, what would we expect?
Very nice. Good question. Good question. So clearly, from the astrophysics point of view, from astrophysical observation point of view, the longer the Broglie wavelength, the better. It's easier, as you said, to resolve these features. And so for astrophysical observation, probably we are limited to axion mass less than about 10 to the minus 20 electron volts. For how about higher masses? For higher masses than that, probably what one should think about rather than astrophysical observation is actually think about axion detection experiments themselves. The axion detection experiments can, of course, probe much smaller scale than what astrophysical observations can probe. And they would be sensitive to wave phenomenology. So that's what I hope to explain towards the end. Yeah, but for astrophysical observations, you're right. You are limited to some basically the ultralight regime.
Yeah, then in this regime, if, for example, we do not really have the resolution to see so much into detail at such small scale,
Yes.
what's the difference then between the wave? Can we really see such wave effects, or if we cannot see such wave effects, what's additional effects we can see?
Well, again, it depends on the mass and the body weighting. Maybe it will be more clear when I get to the astrophysical signatures. How about let's hold off the question, and then then we can talk about it in more detail.
Okay, thanks.
So the short answer to your question is there are interesting gravitational lensing signatures that one could look for, and it looks like those signatures might be observable up to maybe 10 to the minus 20 electron volts. So, but let me come back to that, okay? So I'm going to skip this ahead. I'm going to talk about vortices. Okay, so at first sight, you might say, you know, why do we even talk about vortices? Because I actually told you earlier, you might recall, the velocity is a pure potential flow, right? It's the gradient of a potential. So the vorticity is just zero. So what am I talking about? How can that be vortices? Well, of course, there's a loophole. That's why vortices could exist. And the loophole is actually the following. It's an interesting loophole. If you think about the wave function, it has an amplitude and a phase. At places where you have complete destructive interference, where the density go all the way to zero, the phase is actually ill-defined. And so that actually turns out to be precisely the loophole that allow you to have vortices. So what I want to argue next is that the places where the density turns out to be zero are precisely places where the vorticity is actually non-zero. Okay, so these are what we would call vortices. In our picture, this comes from basically places where just by chance you have complete destructive interference. And you might wonder why we even want to think about that. You might, in fact, the naive expectation would be to say this is very rare. What I also want to show you is that this is actually not rare at all. In fact, it happens actually fairly frequently. So that I also want to show you, okay? Let me just make one comment, which is actually an important comment. If you think about the whole cosmological evolution, in the early universe, you have a roughly homogeneous field with small fluctuations, let's say 10 to the minus 5. And so in the early universe, even though you have waves and they can interfere, in the early universe, you actually do not have complete destructive interference because the amplitude of the waves, these 10 to the minus 5 fluctuations, even if you interfere them, cannot take the density all the way to zero. That's basically impossible. However, if you go to the late universe, when you have order 1 fluctuations, because of gravity, the fluctuation grow, then you have the possibility of complete destructive interference. And as I will show you in the next few minutes, in fact, this is actually an unavoidable and very frequent phenomenon. But this phenomenon really occurs, and I want to stress that in our universe, it happens actually because of gravity. Because gravity amplifies the fluctuations from, let's say, 10 to the minus 5 to order 1 or even larger, okay? And let me also say, most of what I'm going to say in the next few minutes is actually well known in the condensed matter community, basically vortices in superfluid. The only novelty we could claim is that here, this is maybe a little bit unusual situation. Here, the vortices form actually because of gravity, which is usually not the main interaction considered in condensed matter physics. Okay, so let me tell you the argument. This is actually the main argument, this slide. So I'm going to go over it a little bit slowly. The argument is the following. Let's actually first ask ourselves, in 3-dimensional space, what are the set of points generically where both the real and the imaginary parts of the wave function vanish, right? Because that's crucial. We need to look at these places where you have complete destructive interference. Now, what are these set of points? It's very easy to convince yourself at least what is the generic expectation, right? So in three-dimensional space, if you ask me what are the set of points where the real part of the wave function vanishes, it will form a surface generically. And if you ask what are the set of points where the imaginary part also vanishes, is another set of points, which is another surface, basically. Where the two surfaces cross is basically a line. And so even without doing any calculation, generically, you expect the set of points where the wave function vanishes, both the real and imaginary parts, must be in the shape of a line. And this will turn out to be our topological defect. So it's some kind of a string. And so here, this purple line here, I sketch out that string, okay? This is a line where the wave function vanishes. Now, the next part of the argument is to actually think about the phase of the wave function. If you ask how does the phase behave if you wrap around a loop around this string, for the wave function to be single value, the phase must wrap around by integers of 2 pi, and here is an integer. And if you recall how we define the fluid velocity, which is nothing other than the gradient of the phase, this tells you that if you take the velocity and integrate around a loop, any loop, around basically this purple line, you are going to find basically this integer winding, so 2 pi n over n. So the velocity circulation, which is the velocity integrated around a loop, would take this quantized value. And this already tells you this is some kind of a vortex, right? You have non-zero winding.
Sorry, naive question. If where the wave function vanishes, the phase is undefined, right?
Yes,
so,
correct.
Is that an analytic continuation, what you're looking here at, or?
Yeah, I'm looking at the phase away from the purple line. On the purple line, yeah, on the purple line, the phase is ill-defined, as you said. But away from the purple line, the phase is perfectly well-defined.
Ah, okay, yes. Got it, thanks.
and in fact, that's the loophole we are exploiting, precisely. It's basically a topological argument, you know. On the purple line, the phase is ill-defined, but away from it, it is well-defined. And it has to wrap around this way, okay? And in fact, we can say more than that, right? Let's do a Taylor expansion argument. Suppose I pick a point on this line, and I'm going to call that the origin 0, where the wave function vanishes. But let me consider a Taylor expansion for x close to 0. Since the first term vanishes, I have to keep the first order correction, which is basically this term. Let's assume the first gradient does not vanish on the line. It tells us that the wave function scale like linearly with the separation from that point. And if you remember the density is just the wave function square. This tells us the density profile must scale as R square. R is the separation from the vortex. So this tells us that there is a very characteristic density profile around a vortex. It goes like R square. And as you can imagine, knowing this characteristic profile is helpful for looking for these things in astrophysical data, for example. Furthermore, if you think about this circulation formula right here, the right-hand side clearly does not care about the size of the loop. No? I can make the loop bigger and bigger if I want. But this is independent of the size of the loop. The size of the loop does affect this line integral here. And so this tells you the velocity must go like 1 over r. This is also a generic expectation. What I'm telling you in this Taylor expansion argument is for n equals 1, basically single winding. The higher winding basically corresponds to cases where the first order term also happens to vanish, the first gradient vanish, then you have to go to higher order. And you can convince yourself that actually corresponds to higher winding, okay? In which case, rho would go like, for example, r to the 2n, for example. One more comment along this line. The vortex actually cannot actually end. It's kind of like magnetic fields, if you want. This line cannot end, and so generically, what actually it does, it forms the basically a loop. In other words, these are actually vortex rings, and I'll show you pictures of that in a moment from a simulation. And in this audience, probably a lot of you are familiar with axion string, and I want to just emphasize this topological defect I'm talking about here is not the usual axion string, right? The axion string, for example, the QCD axion string, the U1 is basically the Petri-Queen U1, right? Whereas this string that I'm talking about, what is this U1? This U1 actually is a more mundane U1. It's the U1 associated with the conservation of particle number, which you have in the non-relativistic regime. So this vortex is different from the usual axion string. Just want to emphasize that. Okay. And let me show you some pictures. I'm gonna skip this one. Here, what am I showing you? Here, I'm showing you vortex rings that you can identify in a simulation where we just basically allow a halo to collapse. So this is a halo, and over density, under gravity, it collapsed, and eventually it virialized and form a stable halo. And in that halo, we can actually go and just look for these topological defects, these vortex rings, and you can find them. I want to emphasize finding these vortex rings in a numerical simulation is a little bit non-trivial, right? Because remember, the vortex rings are supposed to be places where the wave function precisely vanish. In a numerical simulation, you can never be sure something precisely vanished. There's always numerical noise. And so the more robust thing to do is, in fact, to do something else. You want to check basically the phase. Does it wrap around this ring by these integers of 2 pi? That's what you want to do. That is more robust, and that's what we have done. That's how we identify these rings, okay? And in case you think these rings are always nice, round, like circles like this is a little bit misleading because this is a very symmetric halo. A more realistic halo probably looks something more like this. The rings are more messy. Nonetheless, we could check this standard, this Taylor expansion argument. No? It tells us the density profile. These are basically the density profile around 4 vortex rings. And so we check, does the density goes like the distance square? And it does. You can also check, does the velocity drop like 1 over distance? And it does. So these are borne out by the simulations. Unfortunately, I don't have time to go over these analytic solutions, but they are fun to think about. To give you a sense of the motion of a vortex ring, if I give you a vortex ring so that there's non-zero circulation this way, you can actually show that this vortex ring must, on the whole, move with a velocity. It has a bulk motion, and the ring has a bulk velocity that is inversely proportional to its size. That you can actually also show. And let me skip this movie as well. If we have time later, I can show you that movie. Let me make some comments in the interest of time. First question you are probably going to ask, and I asked that earlier actually myself, should these defects be rare? It turns out they are not rare at all. We can actually check. Roughly speaking, you expect 1 vortex ring per the Broglie volume. That turns out to be a generic expectation. You can check that by brute force by just looking at this simulation and searching for them. That will be a numerical check. You can even actually do an analytical check. If you build a halo out of waves with random phases, you can actually do the computation analytically, and you can actually verify this prediction. Generically, 1 defect per the Broglie volume. And this is true even if your halo overall has no angular momentum, no net rotation. It actually is independent of that. It's really purely a statistical phenomenon. of wave interference. The second point I already went through, these vortex rings move. The third point I think is important to emphasize. These vortices, they are actually transient phenomena. What do I mean by transient? What I mean is the following. If you have a vortex ring somewhere, this vortex ring cannot just arbitrarily disappear. That's impossible by basically topology. However, what it can do is the vortex ring can shrink to 0 size and then disappear. That is allowed. And the vortex rings, of course, can intersect with other vortex rings. So in general, these vortex rings, there's only a finite coherence time if you want. And the coherence time is very easy to estimate. It's basically the de Broglie time. You take the de Broglie wavelength and divide by the typical velocity, you get the de Broglie time. And to give you a sense of scale, if you are in the ultralight regime, the de Broglie time is actually fairly long, millions of years, long enough to give you interesting astrophysical signal. Okay, and I'm going to skip the fourth point about angular momentum and the fifth point, condensed matter literature. I want to use the remaining minutes, if you will bear with me. I think my time is basically over. I want to, if it's okay with you, I'm going to spend maybe a few minutes talking about first, just 2 slides, right? This is one slide on astrophysical signal, and then one slide on signal for axion detection experiment, okay? And hopefully this answer an earlier question about astrophysical signal. So the astrophysical signal are mostly relevant, as I said, in the ultralight regime, basically less than about 10 to the minus 20 electron volts. And there are several things one could focus on. Let me focus on the most promising one. This one, what am I sketching here? This is basically a case where you have gravitational lensing. And in particular, we are interested here in cases where you have strong gravitational lensing. When I say strong, I mean cases where you have multiple images of the same source. In fact, these are the 2 images I sketch here, these 2 stars. It turns out in data, our astronomer friends, they find cases where the 2 images can be highly magnified. They are very, very close to each other. They are close to what we call the critical line. These are cases where the magnification effect can be very extreme, even larger than 100. Okay, and you can show if you have such situation and if the lensing galaxy has a smooth potential, the relative magnification of the 2 images should be 1, meaning they should both be magnified by the same amount. However, if you have substructure, for example, due to this interference pattern that I showed you, that give you the Broglie wavelength smaller than this image separation, it would cause basically one image to be magnified over another. And you can actually do a simple check. A very conservative estimate that we did, kind of a back of envelope estimate, is about 10%, meaning these 2 images would differ in magnification at about the 10% level, which is actually is something that can be observed, can be looked for in data. And a natural question to ask is, if you see this is often called flux anomaly. If you see flux anomaly of this kind, how do you know this is actually due to wave phenomenon as opposed to just particle substructure? Remember, even particle cold dark matter have substructure like subhalos. And the way you can tell the difference between particle and wave is if you are able to measure this flux anomaly as a function of separation between the images. So you'll be measuring the level of substructure as a function of scale. If you are able to measure that, you should be able to tell the difference between particle substructure and wave substructure, because wave substructure has a very characteristic scale, which is the de Broglie scale itself. Okay, so I will just leave it at that, right? In terms of astrophysical signal, there's another sort of astrophysical signal has to do with the scattering of tidal streams in the Milky Way, which unfortunately I have to skip. I do want to end with some thoughts about implication for experiments, because I think it's very interesting, right? Suppose your wave dark matter is not ultralight. Suppose it's 10 to the minus 6 electron volt, yeah, which is the target mass of ADMX, for example. In that case, the Broglie wavelength is about 1/10 of a kilometer. So there's just no way you can see astrophysical signal. It's very hard. As discussed earlier, the resolution just doesn't give you this kind of astronomical data doesn't give you this kind of resolution. However, direct detection experiments actually can probe a lot smaller scale, as you know. Now, what do these experiments do? I don't have time to go over the background. Most of them either use this interaction. This little f, by the way, is the axion decay constant. So either use the interaction of the axion with FF dual of the photon, or the derivative coupling of the axion with basically fermion bilinear. Essentially, this side could be lepton, could be quarks or nucleons. Essentially, it tells you the gradient of the axion is coupled to the spin, if you want, the spin of the fermion. Okay, so there are different experiments that basically use these two interactions. One main point, without going through the details, is these experiments, they all measure kind of different quantities related to the axion. It could be time gradient, it could be spatial gradient. And what I want to emphasize in the light of this wave interference picture is that if you think about an experiment like the ADMX, what do they actually see? What they see should be something like this. So let's say you have a detector at a given location, and you want to ask, as a function of time, what is the axion signal? What does it actually look like? Well, remember, the wave function times this e to the IMT give you the actual axion field. The e to the IMT is basically this fast oscillation, no? This rapid oscillation on this time scale is for 10 to the minus 6 electron volt is on this scale, 10 to the minus 9 seconds. This longer coherence time, which is basically the Broglie time I was referring to earlier, this time comes from basically this side, has slow time variation, and that is around 10 to the minus 3 seconds. The fact that you have this modulation is because of wave interference, and it's stochastic. And the fact that it's stochastic means, in fact, when you think of an axion detection experiment, one should not think of it as if you have oscillation with constant amplitude. It's not like that. This amplitude actually gets modulated by wave interference, the stochastic effect. In fact, the best way to think about axion detection experiment is to think of it as an experiment that measures correlation function. So you can think about, for example, correlation function in time. You can even think about correlation function in space. You can think about what happens if vortices happen to pass through your detector. Sorry about that. If vortices happen to pass through, different experiment actually will see different things. And let me just end with just one thought here. I'm running out of time. The last thought I want to leave with you is, as we discussed earlier, if you have vortices, what is interesting about vortices is the wave function have a phase that have this interesting spatial structure as this winding. At the level of the axion field, it means the oscillation in the axion has this phase, which is theta here. The oscillation phase have this interesting space-time structure. And it would be very interesting to think about what it means for axion detection experiment. Can we use this interesting phase to even maybe enhance our detection signal? That is a thought that I want to leave with you. I'm going to skip over these and just give you a summary. So in this talk, I hope, if anything, I hope I leave you at least with just one idea, right? If you have a dark matter particle lighter than 30 electron volts, you have inevitable wave interference phenomena. I merely gave you one example, which is the example of vortices. In fact, there are many examples. And they give rise to interesting signal. For ultralight, it's interesting astrophysical signal. If it's not ultralight, just merely light, it has interesting implication for axion detection experiments. Thank you for your attention.
Okay, thank you very much for a nice talk. And is there any questions?
I want to ask some question about the vortices.
Yes, please.
For the vortices, I think it's quite not trivial to really simulate the vortices existence in simulations, because at the edge between 0 and 2 pi, I don't know how can it be dealt with when there is such a sharp transition. Do you know?
When you say sharp transition, what do you mean?
So the phase, so around the vortices, so the phase will at some point jump from 2 pi to 0.
Mm-hmm.
Well, how is that done in simulation?
Well, the way you do it is to actually go around in a loop and check the phase actually increased by 2 pi. Of course, when you are at 2 pi, in some sense, you are just saying, well, look, I have this wave function, which is a complex quantity. I have a real and imaginary part, and I want to deduce the angle. At any particular point, the angle is ambiguous, as you know, because I have to invert the cosine and the sine. It's ambiguous up to 2 pi, right? So that ambiguity is always there. What is not ambiguous, however, is the winding. If you actually go around in the loop, do you wrap by 2 pi or do you not? That is unambiguous. That has no ambiguity. I think the discontinuity you are referring to is actually just the usual ambiguity when you invert a cosine. Of course, the angle is always ambiguous by integers of 2 pi. That is always true. No?
Yeah.
That is, I wouldn't say there is a difficulty in simulating vortices though.
Okay, I see.
Does
And
that
one more question is for here, because I know that the simulation was done just solving the we can call Schrödinger boson equation. Then if we solve it, try to use, for example, the Misalignment equation, do you think it's possible to really simulate the behavior of vortices?
Sorry, I didn't hear the first part of what you said.
So currently, the simulation was done by solving Schrödinger boson equation or GPP equation.
Yes.
And if we translate that into Misalignment equation, into the fluid equation, do you think it's possible?
Nice.
To the vortices?
Yeah, that's a very good question. The Misalignment equation is of course very nice because it's a fluid equation, so you could actually just modify a fluid code. Unfortunately, the fluid description actually really does break down at places precisely where you have vortices. And so if you are interested in vortices, you really cannot quite use the fluid equation to study them.
Okay,
yeah. In fact, I can tell you how we even started thinking about vortices to begin with. We started by thinking just like what you were suggesting, no? Let's just put the fluid equation on a computer and solve it. And then we compare against a simulation that solved the Schrödinger equation. And we find that they actually disagree. And we were trying to get to the bottom of exactly why they disagree. And we realized, in fact, it's because of vortices. And in fact, the vortices are very common. We thought they would be very rare, but in fact, they are very common. They're impossible to avoid. Yeah.
Thanks.
Thanks for the question.
Okay, any other questions or comment?
So I have some naive question about the number of vortices you counted. So could you go to this slide?
So let's see.
Previous, yeah.
Which slide? Yeah.
Yeah. So here, you take some maybe natural assumption that the wave had some random phases
Yes,
as the
yes.
initial condition. So my question is how much such a random phase condition is natural or can be obtained from simulation?
That's a great question. So the random phase assumption is something like this. If you have a halo that's well virialized, that's where the random phase approximation is the best, right? So it's the analog of this. So let's imagine you have a bunch of particles that form a halo, and these particles, of course, orbit around the halo. And in general, if you think about a halo that's kind of like, if it's close to being kind of thermalized, then you would think the orbital phase of these particles are basically random. They should not be all rotating around the halo in the same phase. They should be kind of random. And basically, for waves, it translates into basically this phase of the waves being random. Now, in detail, if you look at an actual realistic halo like the Milky Way, for example, the phases are mostly random, but not exactly random, because there are, as you know, if you look at it inside the Milky Way, there are these satellite galaxies. The fact that there are these satellite galaxies, these clumps, small clumps inside the Milky Way, that clump itself is a coherence clump, and so that tells you that the phase is not completely random. Okay. So the random phase is an approximation, and you can check, basically, we check, if I look at simulations, it depends on basically how long ago the halo formed. If it formed a long time ago, the major merger happened a long time ago, then the phase is very random. But if it's a very recently formed galaxy, it might not be super random. So it depends on a little bit on the precise history of the halo.
I see, thank you.
Thanks for asking.
Okay, any other questions or comment?
Maybe I'll stop sharing here so that I can actually see you.
Okay.
Maybe, can I ask a quick question?
Please do.
You didn't talk about much interaction with other particles, but because it's very light. But have you thought about constructing interactions with other particles?
Interaction with particles, in some sense, was what we use when we talk about dark matter detection, right? So there, for sure, to even detect the particle, it has to interact with photons and interact with fermions. So that's what I showed in the last slide. So when you ask about interactions, do you have in mind something else other than detection?
No, for example, standard model particles.
Well, the detection also use standard model particles now. Do you have in mind some? I wonder if you have in mind something else other than those interactions?
Of course, like hidden sector interactions, but yeah.
Right. So there are some constraints. So if you have, if you think about the axion, what we want, because of its origin as basically a ghost storm, so you are constrained to think about basically shift symmetric interactions. And the interaction that I showed you, the phi FF duo, that is shift symmetric. The phi with psi bar gamma mu psi, that is also shift symmetric. So those are the fairly generic expectation for something like the axion. Of course, you don't have to think about the axion. Then you are actually more free, as you said, to consider other interactions that might not even be shift symmetric. So that would be a more general particle, not necessarily an axion-like particle. That's certainly possible. Yeah.
Okay, thank you.
Thanks for asking.
Can I ask another question?
Yeah, please.
I think so. Axion photon conversion also can be detected in the cosmological observation. Then, so this interference, it if that's already is considered or?
Interesting. So when you say axion-photon conversion, which particular context do you have in mind? So for example, let's see, let's think about this, right? So there are people who say, suppose I have a distant source that emits photon. The photon, when it, of course, it will be propagating through the axion field. And in cases where it propagates close to places with large magnetic field, for example, that photon can be converted into axion. Is that what you have in mind?
Yes.
Right. In those computations, typically the assumption is that the axion is just some homogeneous background, typically, or at most it might be boosted by the local density of around some galaxy. The fact that there could be this substructure due to interference is usually not considered, I have to say. Now, how would this interference change those constraints? Would it change those constraints? That's a very interesting question. I think to zero order, it probably would not change those constraints, although I have to think about it. It's an interesting question. Yeah.
Thank you.
I had a question. It's just out of curiosity. So as you mentioned, the vortices may be disappeared by either shrinking the rings or scattered by other rings. But is it possible that some gravitational waves can be created like axion rings?
Nice, nice. These vortices that I talk about mostly they are fairly non-relativistic, so they are not particularly strong sources of gravitational waves, right? However, you could consider special cases. For example, what if I have a vortex close to a black hole, for example? That might be more promising in terms of thinking about emission of gravitational waves. But the generic vortices I'm talking about here, they are not particularly relativistic, so they probably would not be good sources of gravitational waves. Yeah.
I see. All right, thank you.
Yeah, but your question is a good one. How do these vortices behave, for example, close to black holes? It's an interesting question.
I have some questions. So could you show the last slide of your talk?
Okay, and let's go to the last slide. And let's see.
Yes.
You mean the very last one? This one?
Yeah, very last. Yeah. So here you are talking. The third item is about the soliton oscillation, etc. And are you talking about the vortices here? Soliton is the vortices you are talking about, or another soliton?
Yeah. Okay. Good. Thanks for asking. Here is the soliton oscillation refers to something that I did not talk about. In this talk I was only able to talk about actually the very first point. The rest I didn't have time to talk about. The soliton oscillation here is a very interesting phenomenon. It refers to the fact that apparently in these halos, with ultralight dark matter, they have the tendency to form, for the ground state to condense in the middle of a galaxy, forming a soliton. And that's
condensation, BC?
Yeah. That is something that actually happens, and it's purely because of gravitational interaction. It's very interesting. Yeah. But it turns out these solitons are not quite exactly ground state. They actually oscillate, and in fact, they even do random walk around. Yeah, so they have very interesting phenomenology as well. Yeah. That unfortunately I didn't have time to talk about. Yeah.
So does it give any observable consequence or observable effects? Or?
It does. The soliton oscillations and random walk, they have the tendency to heat up stars because they basically causes the gravitational potential to oscillate. And if you have stars there, they actually tend to get heated up. And therefore, it has the potential, for example, to destroy stellar cluster and so on. So you can put constraints, basically, on the existence of this kind of dark matter based on basically possible heating of stars.
So it's not present in the particle dark matter scenario.
That's right. That's right. These oscillations are really specific to having waves. In fact, this oscillation is, again, you can interpret as also due to wave interference. And in fact, the longer the wavelengths, the more pronounced the effect. So it's clear, it's definitely a wave effect. Yeah.
Another question is that what is the effect of the non-gravitational self-interaction of the dark matter phi?
Yeah. The axion, for example, has quartic interaction, as you know, 5 to the 4th.
Yes.
Now there are places in the universe where the self-interaction is actually important. I can tell you at least 2 places where they could be important. One place is important is actually in the early universe. In the early universe, remember, you have this scalar field that initially was stuck where the scalar field value is of the order of axion decay constant. And then only later on it rolled down the hill, right? And so when it was stuck at a relatively large value, the quartic coupling is actually important. So when you compute, for example, the fluctuation in the early universe in this dark matter, you might have to take this into account. So there's one place where you have to take into account the lambda 5/4 coupling. The second place is actually in the late universe. In the late universe, it turns out in some galaxy, a very massive galaxy, the soliton that you form at the center is sufficiently dense that the quartic interaction could be important. And in fact, if the quartic interaction dominates over gravity, then that soliton is even unstable. It would actually collapse. It would collapse all the way to a black hole. So those are at least 2 cases I can think of where the self-interaction can be important.
Okay. Thank you.
Thank you for asking.
So I have some remaining questions. So one is related with the previous questions. So for that kind of discussion, the sign of the self-coupling is very also crucial, right?
The sign, yeah, here we have basically, I'm assuming for axion, it's just come from expanding out that cosine, so it's an attractive interaction. Right. Of course, you could, in principle, consider a repulsive one, yeah.
Right. So then, if we have some positive quartic coupling, then soliton could be still stable, and
then it would be stable. Yeah, the repulsive interaction can counteract gravity.
I see. So
interesting point. Yeah.
Yeah. Another question is, how much some discussion you present here because is different if we take not this scalar dark matter but vector dark matter.
Yeah, the wave interference phenomenon would still be present. So for vector dark matter, it would be the same. The main, I think I would say one main difference between vector dark matter and scalar dark matter is actually in terms of the primordial fluctuations, if you think about it, because as you probably know, in the early universe, if you have vector perturbations, the vector perturbation actually decay, whereas the scalar perturbations actually does not. So that evolution is different, at least one difference between vector and scalar. But in terms of the late time phenomenology, I would say there's probably a lot of similarity. Yeah.
Yes. Thank you.
Thank you.
Okay. If there is no more question, then let's Thanks to Professor Lam Hui.
Thank you.
Thank you very much.
Thank you very much.
Thank you. Thank you for your attention.
Could you send your slide?
Yeah, I can
email?
send you. Yeah. I only noticed now there are some old friends here. I didn't notice before.
Hi, Lam. Good to see you.
Good to see you, Pablo.
Oh,
Where
yeah.
are